Ladies and gentlemen, before the conference begins, please turn off your cellular phones and other communication devices to avoid any interruptions. Thank you. The Mechanical Engineering Department welcomes to the commemoration of the 38th anniversary of our engineer school. This event is being held with the purpose of understanding scientific concepts and contexts about technological development. Our conference today, from the reverse engineering to the simulation in HPC high-performance computer environments, is presented by Mr. Pierre Boulanger, President of Proteus Consulting, Inc. We would like to give a warm greeting to Mr. Boulanger and thank him for his special gesture and important visit to our university. This is a brief review at his curriculum vitae. Mr. Boulanger graduated from Laval University in physics engineering and received his master in physics from the same university and his Ph.D. in electrical engineering from the University of Montreal. He worked for 18 years at the National Research Council of Canada as a senior research officer, where his primary research interests were in 3D computer vision, rapid product development, and virtualized reality systems. Since July 1st, 2001, Mr. Boulanger is working as a professor at the Department of Computer Science at the University of Alberta, doing research and teaching on virtualized reality systems. He is also an adjunct scientist and principal investigator for new media at TR Labs and at the Banff Center. In 2004, Dr. Boulanger was awarded an I-Corps Industrial Chair in Collaborative Virtual Environment. He has published more than 190 scientific papers in various journals and conferences, becoming a member of editorial board of 2 major academic journals. Dr. Boulanger is also on many international committees and frequently gives lectures on rapid product development and virtualized reality. He is also the director of the Advanced Man-Machine Interface Laboratory. On the commercial side, Dr. Boulanger is the president of Proteus Consulting, Inc., an Alberta-based consulting firm specialized in virtual reality applications. We invite now Dr. Boulanger to start his intervention.
Buenas tardes, señores, señores. What we're going to talk today is about reverse engineering, but really about product development. One of the things that we would like to do is to develop new systems that will allow to, from old or previously designed system, to be able to analyze them, to be able to improve them, and to be able to create a more optimal, for example, system. So before I start going into the technical detail, let me present, for those of you who don't know Canada, where I actually work. Basically, this is Canada, and this is the capital, Ottawa. And basically, my university is in Edmonton. It is the capital of the province of Alberta. And the province of Alberta is the province with the oil. So it's some sort of, if you like, the Texas of Canada. This is my backyard. I wish. Almost. Basically, this is the mountain. It's about 3 hours from Edmonton. And this is one of my favorite lakes called Peyto Lake. And it's as you can see, it's quite a beautiful landscape. So the Rockies, it's the beginning of the Rockies to all the way to Vancouver. That's the city of Edmonton. Basically, it's a city of about 1 million people, and fastly growing mainly because of the oil industry is pushing a lot of growth into that region. The University of Alberta is actually has 100-year-old university, which in Canada is a medium-age university. For example, Laval, where I come from, is basically 300 years old. So it's basically there is about 2,500 international students. It's very open to the world. A lot of the grad students are international students. We have about 36,000 students total. Actually, it's more, this statistic's a bit old, it's just more around 44, 45,000. And we offer more than 200 undergrad and 170 graduate program in 18 academic faculties. So that's your comprehensive style university. It's the third university in Canada in the size. So let's go back to the technical side of the talk. Let's take an example where we want to design something, and we want to design it so that we have a certain set of business target that we want to reach. Because engineering, as you know, is never separate from the business aspect of fabrication and the production. One of the key things in engineering is when you make a product is time to market. For example, if you invent this laser pointer and you're the only one on the market to have this laser pointer, you want to be fast on the market so that you can actually sell this laser pointer at a high price, make a lot of profit, and before other people actually start producing them. So part of the business aspect that actually have linked to engineering is a demand for reduced lead time. I mean, you want from the start of the project to the end of the project, shrink that as possible. One thing that is happening today, which is very common, is an increased product variety and quality requirement. We are getting away slowly out of the mass market production, and we're entering through rapid product development toward more the adapted product. You design your own product, and eventually I'm going to go into a website and design my own laser pointer that I like, and we will produce that at the same cost as if you were mass producing them, and that's done with this type of technology. Of course, I mean, you all know about worldwide competition. I mean, Chinese competition where the cost of labor is so low that it brings down the prices, but actually this is changing quite a bit. In many ways, the Chinese economy is based on the old economy where it's mass production. This will change as the technology will advance. As technology becomes more sophisticated, we will have production that are closer to the market, and also we will have adaptable production. Which means that actually in practice we will have smaller runs, but we want to produce things at the same cost as mass production. So we have to find technique and ways to go from the engineering design to the production that will have the same cost and impact as mass production. Yes? Okay, that's good. So, and of course, you want to have just-in-time manufacturing so that basically you receive your product and you don't have to do warehousing. Okay. So what are the enabling technology? I mean, I'm an engineer after all, I'm not a businessman. So what are the enabling technology to allow you to do that dream of creating adaptable, flexible factory that would actually produce locally objects that you actually may eventually design in your own home? Well, certainly we will have to have computed technology, I mean CAD systems, rapid prototyping machine, conversion technology. What we're going to talk today is about the other technology that if you go to any meeting in rapid product development, that are the three main things that people focus on. But what we want to do is being able to sometimes take old design and bring it to become new design. And so we have to have a process called reverse engineering, which will allow us to capture the design and bring it to modern standards, for example. Because the design might work quite well, it's just we just want to do how to mass produce it. So we're going to talk today about this process of reverse engineering, and we're also going to talk about the process of dimensional validation, where we want to mass produce things. And in order to mass produce things at well, not to produce in small batches, but at the same quality as mass production, we will have to deal with dimensional validation. And in order to do that, we have to have 3D laser scanners or three-dimensional measuring devices that allow you to take the shape. And then after that, once you take the real world and brought it in the virtual world, then anything you can do. I mean, it becomes some sort of, but the difference between gamers and engineers is the virtual world has to be accurate. It has to represent the real world. And that's the big difference. And that's what makes it harder in order to represent. But a lot of the technology that is used by gamers, and actually enough, the gamers are helping the technology of the virtual prototyping to improve, is that we want to achieve this accuracy or representation of the real world and make sure that what we simulate in the virtual world is a representation, because actually at the end of the day we're going to use it or machine it. So in a context of rapid product development, we're going to see during the talk many loops of different operation that you do. One of it could be that you are a designer and you'd invented a very nicely shaped laser pointer, something much nicer than this. You might have done it in clay model. You're just an artist. You are not someone who is good at CAD, or you don't even want to be part of a good CAD. You are good at making nice shaped object. So how do we, from a prototype, bring it in the virtual world using sensors, and then from that being able to go into a reverse engineering process, being able to go to a CAD-CAM systems, and then once you're in the CAD-CAM system, then be able to perform machining or perform three-dimensional stereolithography and allow you to produce small batches of this object. So once you've done that, of course, as all of you are engineers, when you actually produce something, it's never as good as you think it would be. There's limitation of production. So you want to go back again into the system and be able to inspect your object and find out that, for example, that once you put the engineering constraints on the object, you might have to modify the shape of the object. For example, the artist might like this bend on the object, but when you actually drop it on the floor, it actually breaks. So maybe there's a price that have to be negotiated between the designer, the artist, and the engineers. So, and you have to have an environment where you can actually negotiate that process. So basically, it's actually this drawing here is from when I used to be at the National Research Council. It's actually 20 years old, and I'm still working on it. There's a lot of company like, for example, Daimler-Benz, and which I work with, and HP and so on, that actually are still working on creating this dream of this flexible manufacturing process or rapid product development process. So first step is to take the real world and bring it in the virtual world. How do we do that? Well, there's many ways to do that, and we're going to see that there are tons of sensors out there that can be used to achieve that. But we're actually going to look at only a few of them. A mechanical triangulation system. One is a photogrammetry. It's actually at EAFIT. And the third one is an industrial tomography, which are starting to be the new standard, able to digitize objects from the real world to the virtual world, as tomography will allow you to get the outside and the inside structures. In the world of metrology, in the world of dimensional digitization, there is a whole slew of physical principles you can use in order to measure things. The first one is actually what carpenter use. I mean, a rope, a level, a laser that put a line. I mean, they build pyramids. But as time goes on, I mean, we need more advanced measuring devices, and these measuring devices system, depending if you're throwing energy to them, using structured information like my laser running to the wall here, which allow me to track easily that object and measure its position in 3D space. So there are many devices that you can find in industry, and I'm just telling you, I'm showing you that as an example of the quantity of three-dimensional scanning device you can actually find. There, if you look on the websites and something like this, you're going to find hundreds of them. They're not all equal. So let's take first the one that we have in our lab. It's basically a three-dimensional laser scanner, which basically sends a line of laser. It's a scanning line of laser. And there is a scanning line laser that comes from here, and there's actually a camera that's looking at that. And then from that, we can actually, by the old principle of Pythagoras, if you know a position, which you do from the laser, if you know a distance and you know two angles, you can actually measure. It's a simple triangle, and you can actually measure where this point here falls onto the surface of the object. So laser triangulation or triangulation principles are used as old as it is. I mean, that's from the Pythagoras time. As old as it is still used today in a more electronic form, usually by sending lasers. But actually, if you take passive system, for example, stereo system, in many ways, it is the same idea of triangulation. So typically, those sensors will give you in the order of 35,000 points per second, so it's very fast, at a resolution of 50 micron. The real precision, on the other hand, is usually a bit lower because we also have the sensor mounted on the very precise arm. It's called a Faro arm. And with that, we can actually position the sensor around the object. Because as you can imagine, if you're digitizing an object, there's a lot of small corners, there's a lot of small things, small regions that you will not be able to see, and you have to more or less position yourself to see them. So with this arm, you can know exactly at all time where is the sensor relative to some central coordinate system locating at the base of the arm. In addition, that laser scanner has a touch probe that allow you to get to places that are impossible for the laser scanner to get, or if let's say you have glass, you can see to glass. You can measure glass because it's unless you paint them. And then in this particular instance here, we actually doing that for an museum application. We're also using a color camera to get the color shape or the color information. So typically, you'll get information like this one. So Nefertari statuette, and here's the three-dimensional data. You can see them as a wireframe here. Now you can see it as a dense range or distance information. So you got all the views put together and integrated. And here is the colored version of that little statuette. So of course, I mean, one of the application is if you have an object like this one, or a more artistic object that you want to have reproduced with good quality, you might want to use machining system for doing the shape, and you might want automated painting system to actually put the color into it. And you can actually make, for example, take Museo d'Oro, beautiful jewelry. I mean, you might want to make nice high quality copies from that. Here's some picture that actually of a system that I saw this week. Basically, one of the reasons I'm here is to evaluate the project of reverse engineering a turbine for APMA. And in this system, it's using another principle where now, instead of having an arm to measure where the sensor is, this arm, we're now using a set of targets, and we're using something called a photogrammetric system. So basically, there's a camera looking at those targets, and it's determining what is the orientation and the position of that sensor relative to the object. So of course, if you want to digitize an entire object, what you're going to have to do first is to lay a whole series of targets onto the object, like Carlos does here. And basically you go and digitize that object, and the object itself, the shape itself, is determined by triangulation. Again, in this case, it's not just a line, it's a cross of lasers that actually does that. So the scanning mechanism is the same, except in this case, the positioning the mechanism is now a photogrammetric positioning mechanism. Precision on that is in the order of 0.2 to 0.3 millimeter into that. Actually, they have a new system that actually will give you in the order of 30 to 50 micron, which is enough for plastic and some big object like this, certainly not enough for, say, high-end machining. So here's the model that Carlos produced. I mean, it's a complete model. And he can certainly tell you how hard it is to solve all the views, especially this object was a real bugger. It was, you could not put the sensor inside, so you had to basically create molds to extract, make the object. But he was able to produce this very high quality model. Other sensors, because the complexity of creating models, because you have to take all these views, people came up quite a while ago, the same idea as, for example, when we actually go and do medical CT, where actually we have a fan beam going to, normally it will be your body, and there will be an array of detector, and you just rotate the fan beam around you and move and basically produce something called a tomography. So what is a tomography is basically you try to infer what was the density inside the material that actually produced the absorption of the X-ray that was detected by this array. And there is a special algorithm called a tomography algorithm that actually allow you to determine that absorption. So you get a cross section, and it shows you, in this case it's a beam, a tube, and you got the air, which has no absorption. You got the metal that has a high absorption, and then you got air inside again. These systems have become quite low cost. I mean, you can imagine, we don't want to put a $1 million to $2 million laser CT scanner for scanning little art object or some basically object from a, let's say, a manufacturing company. So there is a whole slew now of these so-called tabletop CT scanner. They actually produce X-ray, and they actually move the object in front of the X-ray, and they get this type of data. Actually, you get a precision for certain type of material that are in the order of 0.1 millimeter. And the advantage of that is when we go to the next step, which is moving from the scanned data to the virtual simulation, we're going to see that actually in many ways these X-ray CT scanners are adapted because they're very close to finite element, to a volumetric representation. The other thing is there are many objects we have internal cavity that are impossible to see with laser scanners. So for example, in the case of the turbine, assuming that money was no object, there are actually industrial CT scanner that can actually go to about 6 feet of metal. So for example, you can put a turbine like this, and in an hour you got a 3D model of the turbine. But those systems are $10 million, so it's be hard to justify the project. But like I said, for certain size of object, for example, those machines are in the order of 50,000, 60,000, which is more or less the same price as laser scanner, high-end laser scanner. So what can we do with this data set? Once we've digitized the real world, what can we do? Well, let's look first at the first possible thing that an engineer would think is, I'm designing this, I got that in my computer as a CAD design. I'm asking someone somewhere in the world to machine this and create the object. And then it comes back as maybe 1,000 or 1,000,000 of those little things. And I want to know how different they are from my original CAD model. So you're going to have a process called inspection. And laser scanners and CT scanners allow you to simplify a lot of this inspection process. So the normal inspection process is the following. So basically, you scan your object that you receive. You got your model. You create your three-dimensional model. And once you got your three-dimensional model, then you take a reference model, which is your CAD model, and then you perform an alignment between the two. And once you got that, then you can actually make a comparison and see what are the production defects. Problem is, a lot of objects today are flexible. In a sense, they're more and more composite material. Even metal, like a door like this, if you actually put it on the floor, it warps. So if I'm going to do this here and actually assume that it's all rigid, I'm going to have the illusion that it is not intolerance, as in fact it is intolerance. So what usually people in manufacturing do is do the following. They take your part, they fixture it, which is put the anchor point as if it was going to be installed in, say, this is a cover of a motor. So as it is installed using clamp, and then they perform the scan, then they unmount it, and then they pick it up, and then they actually then perform the comparison, because now you've put the part in its nominal position and how it should be. For example, in the Airbus 380 and the Dreamliner, not to make people unhappy, from Boeing or Airbus, all the airplane is built more or less in composite material. Well, one of the biggest problems they have is composite material. When you take them out of the mold, they spring back. They are actually deformed. Every part in an airplane has to be inspected. So you imagine you have to take every part, fixture them, laser scan them, determine how much they are relative to tolerance, and then when you actually put them back into the airplane or assemble them, you have to attach them with the rivets. Well, and there was so much problem with that. Actually, last year, Boeing ran out of rivets. The whole corporation ran out of rivets, assembling the Dreamliner. And it's the same for the French. They had this problem, and that's why all the production are delayed. So this is quite a current problem of inspection of deformable object. So what we would like to do, and actually show you in some way in a nutshell, as I'm going to show you a bit later on, what is the importance of virtualizing the world. That's the word I'm going to use, which is taking the real world, bringing it in virtual world, and then doing virtual experiment to it. Here's an example. You're basically going to scan the part, just put on the table, scan it like it was at nominal position. Put virtual constraints on the part. And then once you put the virtual constraint, use either a finite element model or another type of model, which is polygon morphing, which is, I'll talk to you in a moment. And then you perform the comparison. So now you've basically opened the door to automated inspection, because you just throw on a table, a robot can just go and scan it, and a green light comes on, or a red light comes on, saying it's intolerance or it's not intolerance. So in order to do that, and actually it's a project that we've done with Manuel Garcia, where basically it was financed by Precarn, which is it's basically a private company, Creaform, which is another private company, University of Alberta, Laval University, which is basically the inventor of the scanner, the handheld scanner, and basically EAFIT University. So what did we do? Okay, so here's your CAD model. So that's basically your original CAD model. And at the beginning, that's how the part looked like. This is the CAD model, this is the part. It's quite distorted. So one way to do it is to do a technique called polygon morphing, where you actually pair points, and you say those points are the same, as telling those points are the same, and then you're going to move the cap toward it by simple interpolation distortion. Here we are, we're moving the cap. Bingo, we're on top. Now we can take this and we can inspect. Here's the inspection report. And actually, initially I thought there was a defect of the method here, but it turned out, in order to distort that part, they actually took a blowtorch. And actually they distorted not in an elastic mode, they actually distorted in a plastic mode, which is, for that method, certainly not what it is planned for. So basically, from that, you can then determine everywhere around that part if it's intolerance or not, by using a color map or by having hardcore engineering specification to the part. So there basically that method in particular is very easy to implement. But basically the big defect, it doesn't represent very well. It fits with the property of the material. So it would be in some way useful for certain type of object that you know the object are not going to change too much in material, and they're not going to be too much change in the material. But if you have objects where there's a real change in material, certainly in this type of technique, and it doesn't follow one of my cardinal rule, it's not following one of the physics law. I'm a physicist in background, and when I do simulation, I want my simulation to follow the rule of physics, because otherwise you're in some never land that might look good, but it is not necessarily something that actually is accurate. So that's why we decided, even though it looks like it's working, and it's a nice example here, it looks like it's working, but it's not following some physical law. So the next thing we decided to do, and it was Manuel, we decided to apply shell element technique to this, finite element. And then idea is to apply either a force or a displacement to the object, same corresponding point, and then we have shell element like this one that actually are applied. And think of it, I mean, the one that you saw before, it will be the same, but except now it is physically accurate. As it is, we have the Young modulus of the material, we also the Poisson modulus, we know the property of the material. If the material change, we can determine that. And the other advantage is when there's a discrepancy between the fitted data and the information, we can actually use that to infer that maybe the object has not the mechanical property that it should have, and maybe we should look further. And that's certainly one advantage of sticking to physical simulation. So in order to create those nice model that you actually can use for simulation like we just did, we have to go to quite a lengthy process of so-called reverse engineering. And I'm not going to go into all the detail of that process. I'm going to show you actually example of it. But basically, in a nutshell, you use your laser scanner, you get points from different views, you basically register those points, and then you create a triangulated model. And then you do what any engineer would do in a CAD system. You lay a network of surfaces, you clean them up, and then you basically create, at the end, a proper CAD model of the object. It's very time consuming, and I've worked quite a bit along the years, tried to automate that process, and we've actually most recently, we've developed a special quadrilaterization, that's a hard word, algorithm, which allow you to do some automation of that. So, but instead, let me give you an example of practical reverse engineering. So here's a toy, a handmade toy, could be anywhere, and we take the multiple view, we register them, here it is. After registration, there's always going to be places where we don't see. I mean, it's a bit like Carlos' turbine. There are places you don't see, and the laser scanner cannot get there. And then we have to have a way to fill them up. I mean, in this case, we could actually fill them up like here. And then, in this particular case, they were interested to keep the head, but the lower part, they want actually a clean CAD-like surface. And so basically, they put that clean CAD-like surface. And it was for injection molding. So basically, for those of you who don't know, injection molding typically is done into steel plates that are very hard. So typically, they are machined first a copper electrode, and by the process of electrophoresis, they will actually machine the plate with the discharge. So we were able to do that in 2 weeks. Before, this person who does that had to take your object and actually send it in Asia somewhere where they will use something called a pantograph and actually make copies of that object into creating this. And as you can imagine, the precision and the resolution of that is not that great. So you don't have, you would lose a lot of the detail of the artist, in this case, who created the toy. Here's another example. That's actually what we did that at the National Research Council. Here's another laser scanner, and then we digitize the Sphinx. It's actually a copy of a Sphinx. And we were able to make copies. And through a process called stereolithography, where we can actually print in 3D, we were able to make molds. And actually, that stereolithography model, or those molds, were used to produce artifacts that were actually sold at the museum. Most of you might have seen Sphinx that are sold by hand sculpturing in shops, and you can see they're very, very poor compared to the original Sphinx. And those one, in this particular process here, we can actually make very accurate copies. So accurate that actually we, for certain cases, other cases, we actually have to add some defects in it, so we can actually identify knowing it's a copy. And it's crazy, but that's how you have to do that. Another example, and then after that we'll move to simulation, because actually it's an intro to simulation. Actually, one of my students did that a year ago. He had the watch, and it kept on breaking every time. He liked that watch, and he keeps on breaking here. And he wondered why. Why does it break here? So basically, we scan the object from different views, get the 3D models, cloud a point. Then, to a process called reverse engineering / reconstruction, we were able to reconstruct the bracelet here by using some we knew the bracelet was symmetrical in some section, so we wrapped it around, and then we were able to virtually repair the bracelet, and then we had basically a tetrahedral mesh produced on that. So the next step is, the question was, why does it break? Well, now we got to go into the world of virtual prototyping, where we're going to apply rules of physics into those real models in order to understand what goes on into the real world. So basically, once a 3D model is created, it allows us to do infinite amount of testing on it. I mean, there's no limit on that. It will also allow us to, for shape and functional optimization, it will allow us to track the complete life cycle of a product. As in a factory, you start machining things or you start producing things. Frequently, at the end of the day, this pen here, high likely, is very different from the original CAD model. Very different. Problem in factories is the CAD model stays in the engineering section, and the mold that produced this, or yeah, that will be more of a extrusion thing, but the mold, let's say that's plastic, so this is extrusion, the extrusion mold wears out, and so you're going to have to again machine again, or you might find that you want to reuse some of those molds for other applications. So what you can do with this particular reverse engineering and tracking and virtual simulation is you can actually track the life cycle of the product, which is very important for factories. And once you do that, you can actually create a complete documentation of the entire process that goes on in the factory, and try to optimize those processes. And that's also very important. Is many times, especially if you're using die casting process, you basically will change the temperature of the die cast, inject aluminum, and try to get a shape that is accurate. A lot of it is a grand art. It's actually not even science. It's really technicians being so good at it, they have in their mind a virtual simulator that some sort of know that if you put temperature there, the aluminum will go through the cavity. If you don't put it there, it will freeze before it goes into the cavity. Or if you put a vent there, what happens is it's going to be, if you don't put the vent, it's going to be air mixing with aluminum, and you get porosity problem. So there's a die cast, let's say, of an engine, easily take before it's tuned in the order of 6 months to be able to be safe. You can actually do mass production. You can also, again, through virtual prototyping, virtual simulation, you can reduce that significantly. One thing we're going to see, though, is we're going to need a lot of compute power to do that. If we want to simulate the real world, we need a lot of compute power. Because the real world, in many ways, if you see that as a computer, it's an enormous computer, as things interacting with each other. So back to our watch. So basically, my student did what you would expect. So he put his virtual wrist there, and he had a force in X and a force in Y, and he would apply the force in X, and whoa, if you look at the strain on the watch here from the finite element simulation, oh, how surprising. The maximum of the strain is exactly where it breaks. That's, in this case, in the X, so it's actually not due to the X direction, which is bound to be expected. It's really due to the force in the Y direction. And what was the last one? Oh yeah, that's applied in both directions. So in both directions, there is not problem. So obviously, when the person wear the watch, if it gets caught somewhere and pulled in the X direction, which is very easy to cut your watch this way, this is the reason why it breaks. So we answered the question. The other question is, how can we take this and make a better watch? Well, we can actually take this watch, now we have a model, and we can do optimization of the shape so that we actually try to reduce that strain. So when Manuel was in Alberta, we actually did it with a part that turned out to be actually pretty optimal, actually. We tried to optimize it, but actually it was quite optimal. Here's a BL, crankshaft in English. The question here was, how can we improve the design of a crankshaft? So basically, the original crankshaft, the cloud of point, the reconstructed model, we reverse engineered it, and here's the strain or the stress apparatus. So it's the stress distribution here. And then, actually, Manuel had programs where you can actually change the parameter of the CAD here and actually try to minimize those stress here inside the BL, or the crankshaft. So again, we can actually take the real world, bring it in the virtual world, test to know why it's not working, and also try to improve the design. Another example. I'll show you. I usually do my talks by example. Here's another example. This is a typical clutch fork. There's a cylinder, and it's pushing when you push the clutch, and it's pushing on the transmission here. Well, there was a Ford truck clutch, and the Ford are renowned to have the clutch that breaks, the fork usually here. Well, we applied the same rule. Make a 3D model, try to understand the model, apply stress. But initially in the model, we apply the forces like in the drawing, forces on both ends here. Well, we couldn't see any problem. It was actually the maximum stress was around here, which is a thick part of the metal, so there shouldn't be any problem. So I forgot who, I think it's who found that? Miguel. He actually had a very good idea. He actually said, okay, let's measure this point here, let's measure this point here, and he found out that in the original model, there was actually a discrepancy between this point here. So basically, the fork was not flat at the contact point here. So very likely, when the clutch was pushing at one part of the time, a fraction of a second maybe, the clutch was actually pushing only from this side and not the other side. If you actually put the stress now only on this side, whoops, we got the maximum here where it actually breaks. So we got now the explanation for that. The next step is, how do you fix that? Well, actually, originally the manufacturer went to a bizarre process of putting a lot of metal here to actually improve that. But it turned out that you don't have to do that. You just have to grind so that it's flat. And it's actually, when it actually hit that piece of metal here, it actually hit it at the same time. in many ways, someone could say, well, this is a bad design. Maybe this here should not be a separate thing. It should be something like a plate or something that do that. But certainly, we were able to diagnose why it doesn't work, or why it breaks, actually. And then maybe it suggests some. So we're doing quite a bit of engineering here still. I mean, we're understanding why something doesn't work, and we're trying to find a new design that actually allow you to fix that. So those are small examples of the type of thing you can do with your basic reverse engineering. But what we really would like to do is being able to perform simulation and basically design together, in a sense that I'm going to have a virtual model, let's say, of this cup, and I basically going to change interactively in the CAD the shape of the cup and try to determine what is, for example, the drag factor, not a cup, let's say a wing, what is the drag factor of the wing as you modify it. And if you separate too long the change with the actual result of the simulation, what happens is there's a decoupling. You lose something called insights. An engineer wants to have insights. He has, like I said, this little simulator in his head. He understands his problem. He knows that, but in order to do that, we have to break the barrier of computation that this simulation requires. And we also have to create new type of environment that are virtual environment, virtual experimental environment that allow us to interact with those simulations. So about 3 or 4 years ago, we decided to embark on a huge project, which is basically the so-called virtual wind tunnel project. The idea was to create the equivalent of a virtual tunnel, and the reason for that is a virtual wind tunnel is incredibly expensive. A small one, a baby wind tunnel, is in the order of $100,000. And that's not even, you cannot do that much with that. So how can we use the power, the new power of computers and visualization, three-dimensional visualization, to perform optimization like we just did here? I mean, optimizing the shape, optimizing the reducing stress into things, and so on. So here's the concept prototype here. So again, we got the same idea, which is typically the flow of simulation that would normally do in any process of fluid dynamic or CFD is basically you got your CAD model. It could be laser scan. For example, in the case of the turbine, this is a laser scan model. You go into a meshing process. You go to you specify boundary condition, wind direction, and so on. And for example, you apply CFD into that, and then you visualize the information, and you try to deduce information from that. So a lot of it you have to think is you're going to have a massive amount of data point coming to possibly by supercomputers, and maybe terabyte of points, and you have to also visualize them so that you can actually make sense out of them. So just give you an example of a typical, again in the same scheme, basically this is a terrain model. Basically NASA about in 2001 digitized the entire planet, and basically we took a region, Mount St. Helens, and we created a model, and we created a volumetric model that allows us to apply CFD to it. And I won't bore you with the detail, but basically we had to do some form of surface reconstruction, specify boundary condition to the mesh, and mesh conversion, send that to a software called OpenFOAM, and basically look at or solve the problem. This is what we obtained, basically a laminar flow going to Mount St. Helens, and then you basically here you can see that there are some turbulence going on at the tip of the mountain. In some way, actually, this is amazing. We can actually take any place on the planet, we can actually determine what is the low altitude wind. So if you're going to place, for example, windmill in a region, you can actually use this type of information. So some sort of knowingly at the same time, we actually created, I think, a very powerful tool here for people who want to actually place windmills or want to reduce placement of buildings around, for example, landscapes and so on. And actually, we started one project at one time where we actually took, with Manuel, we took basically infrared Landsat, which gives you the temperature of the land. This is actually the Valley of Medellin, and basically we take the 3D data, and through a buoyancy model in OpenFOAM, we can actually determine how the buoyancy, not the buoyancy, but convection current are actually happening in the Valley of Medellin. Eventually, the idea would be to create a, for example, a pollution model of, you could put different chimney stack, and then determine how do pollution propagate in the valley. All that from simulation. I took from the recent work Manuel did here with the turbine. So again, we have in this case a process where we have the real world. We specify as best as we can the boundary condition, which is basically what we think the real world is influenced by, and then we perform the simulation using relatively accurate laws of physics, and then we try to observe and try to optimize patterns. So for example, in this particular case here, the purpose is to optimize eventually the shape of the turbine, that's built turbine, into a better turbine. So part of the process is the interaction of the engineer with the simulation. In a real world tunnel, you basically you can rotate the object, you can put pitot tubes at different places, you can go and make all sort of measurement. We would like to replicate that. So basically in the system, and actually I'm going to put this slide first, in the system we want an interface, a so-called multimodal interface, which will allow you to perform all these interaction that you would normally do in a virtual wind tunnel, in a real wind tunnel, and maybe more. Maybe you want to hear the wind. Maybe you want to feel the wind as if your finger was in the wind tunnel. And one thing that we just did, and Maria here is truly our specialist in multimodal interface, where we were using visual but also sound rendering and also haptic rendering. And for example, in the particular instance of haptics, we can actually have the perception of fluid flow, we can have object manipulation, and also we can set the boundary condition. We can, for example, change the wind orientation in that case. In the case of fluid, sonification of fluid, for example, we found out it is very useful to find eddies and find turbulence region, which is very important for any wing design, for example. And it's very difficult to see if you only use visual. Most fluid dynamicists stick to that, this mess of arrow that is basically a visual representation. But by adding more modality, because we are multimodal as human beings, I hear, I touch, and I see, the computer has to transpose this information that is a numerical information in the computer back into that. But coming back to that drawing here, we have to put that back in the context of interactive CFD. So basically, typically in CFD, you got a preprocessor, you got a solver, and a post-processor. That's your minimalist view of a CFD process. Well, where does a human have interaction with that? Well, you can maybe define the geometry, discretize the geometry, meaning the mesh, set boundary condition, and change physical model, for example, change the viscosity or the temperature of the fluid. You solve, basically that's something that should be automated, and then you have a post-process, which is usually a conversion from what come out of a fluid dynamics process to some visual representation or auditory or haptic representation. And then the person decides is happy with that, and then book loops again, and that's where the engineering loops comes in, where you try to optimize, for example, the shape of a wing, or for example, the design of a turbine, as in this project. So one Duque, one of Manuel's students, did a prototype of that where he actually had a little car, and he was able to change the orientation of the car, set different wind orientation. It was a nice little prototype that we can actually now take and bring it to the next step, which is a much more user control. This was done by scripts and things like this. We just wanted to know actually how the solver responded to the human interaction in this. In some way, this is not that different than flight simulators. Flight simulators are advanced simulation environment. They actually even have fluid dynamic part of that. And what you're doing is you're controlling this environment, and of course the concept here is to do design. So we want to change the shape of the motor of the car here, or put some fin or whatever you want to do as a design. But you want to do it as if you're doing it like if you would do in the real life. Okay. We're almost done. So the next step is engineers do not work, and that's a general statement here, engineers really rarely work alone in their office. As you work in a big engineering firm, you're going to have a zillion amount of meetings. You're going to fly around the world non-stop. Well, maybe with those tools, we can actually reduce that and increase the efficiency of the collaborative design process. So the idea is to use some of those tools to distribute through a high-speed network those tools, to create services, and then being able to be at different places and having access to those things. So in another instance of this, not the fluid dynamics, it's actually our Earth simulation. We had a simulation that was actually running on a supercomputer, a 256 CPU machine, and we had people in Toronto, UBC. This is 4,000 kilometers apart, using the Canadian high-speed network, and all these people were part of the meeting, could actually modify the solution, could change the solution, could take different viewpoints to the solution, and actually could talk to each other. All that being able to annotate things. What does it mean is that now globalism can actually be applied to engineering practice, in the sense that now an engineer in Colombia, an engineer in China, an engineer in Paris, and in Canada, you try to locate the engineer that has the expertise. And expertise is not evenly distributed there. Expertise is everywhere in the world. Being able to interconnect, being able to share tools that only in the past rich and big corporations could afford, and they don't move from those places, they're just being shared through the network. So for example, one of the things that we have part of the new project, which will open tomorrow officially, is the Renata project on the virtual wind tunnel that's headed by Manuel. And one of the things that myself, I would like to do, outside of the fluid dynamics and the simulation and all the technical detail of connecting the dots, is someone in Medellin, someone in Los Andes, actually Pablo Figueroa from Los Andes participating in that project, someone like me in Edmonton, and someone in a group that we work in Paris from the LIMSI, all interconnected together through the one common thing, which is the high-speed network. And in many ways, that demo will be very interesting, because collaborative design through basically three networks: Canary, Renata, and Géant. Géant being the European equivalent of high-speed network. The park, and I'm coming now to the last part of the talk, which is, in order to do what I'm talking about, we need, unfortunately, at least a teraflop. Well, that doesn't, we all think that we have powerful computers at home. Those are toys. We want 1 million times faster. We want at least maybe 10 million times faster. Fortunately, we are born in the right years, in the sense that I'm going to show you a curve of amazing consequence for our project, which is actually the curve of processing power of something you find quite weird, which is the graphic board of gamers. we can actually make teraflop machine out of those machines. By combining cluster computers with GPU, graphic processing unit, we can create those teraflop machines which allow us to perform all we were talking about, which is this virtual wind tunnel. At the beginning of the project, we were using your traditional grid environment. We have a grid project in Canada called WestGrid, and they were a whole park of computers. I mean, I won't cite them, but one, the computer we were using is this one, a 256 CPU machine. Sounds big, but you know, when you actually add it, look at the problem with those machines. 700 megahertz, IP35. Well, you got a faster machine now on your desk now, or in your laptop. So a machine that may have cost close to $1 million is, after 3 or 4 years, obsolete. Same here. This is the new machine we have at our service for the project. Actually, the nice thing is we're not sharing it, it's actually ours. We have a 64 Itanium CPU machine with 35 gigabit NUMA bus. One of the nice things now with a new bus, especially from Silicon Graphics, is the problem when you start to do parallel processing is the inter-process communication becomes sometimes larger than computation. So you mean, more or less you mean is you're talking more than you're actually thinking, which is something that happens in life frequently. But associated with that, we have 6 ATI graphic card, gamers card, and we have a large memory because we do need large memory, a large disk because these are big projects, and we have 2 FPGA node, which is programmable hardware. But I won't talk about that. I'll talk about mainly this ATI card. Look at the curve of compute power as a function of time. This is your basically CPU in your machine, and it's actually the CPU very much in the supercomputer too. Is now today the manufacturer use commodity CPU in the supercomputer as well. So if the CPU on your desk goes up, the supercomputer goes up by the same proportion. But look, we're reaching the limit of Moore's law. The one way to get away from Moore's law is to put more core, meaning more CPU in the same chip. We're now 2, move to 4, and actually SGI and Intel have now released an 8-core CPU. But to look at the game board, or the video board, I want to emphasize the game board because it's amazing how gaming actually, out of the blue, is helping serious engineering work. Here it is, basically the NVIDIA 8800 is now at a speed of 380 gigaflop. I put 4 of those cards, I got my teraflop. The card costs $2,000. So now, with 6 of those cards in this project, we can actually achieve this teraflop computing power. And the way to do that is called this basically this type of equation you find in fluid dynamics. I mean, heat transfer and conservation of masses and moment. But typically, you got your CPU communicating with the GPU, graphic processing unit, your video cards. And inside the video card now is they're reprogrammable, and they don't call it GPU anymore. They call it GPGPU, which is general purpose graphic processing unit. And there's a special language called CUDA that actually allow you to program them. And then in each of them, for example, 1 pixel, that might be floating point, you might have 128 processor for 1 point. So imagine the compute power of those things. Eventually, and ATI, which used to be a typical Canadian story, ATI, Canadian company, got purchased as usual by an American company. But nonetheless, an interesting combination. It's not AMD purchased ATI, and Intel has a very big relationship with NVIDIA. The next computer are going to be 8-core machine with maybe 2 or 3 GPU on the side. So you're going to get an incredible power, teraflop power, and once you get into the teraflop world, optimization, finite element, and all this, all that we think were batch mode type thing now can become real-time thing, that we can actually do real-time optimization with them. I mean, putting again the human brain into optimizing shapes and optimization process. So that's really what we're up to now. In the sense, we're trying to start. Well, tomorrow is the Colombian side of the opening of the Colombian side of the virtual wind tunnel, and our goal is to reach this virtual wind tunnel. And we're not going to just do virtual wind tunnel. Actually, we're going to do also finite element and optimization. Virtual wind tunnel is just a pretext to develop this real-time experimental environment based on computers. So in order to tie all this together, I mean, we're running out of time here. Basically, we developed some server. It's a bit techy here, where basically we have an environment where we can have multiple people connecting, and we can actually create services and basically communicate with those services. But this basically reside in the supercomputer, and you don't see them. And so someone comes in, he doesn't have to reinvent the wheel. It's basically all the services that I've just discussed for visualization, simulation, control of the mesh, and all that is available as is. So, not too bad. Basically, our ambitious goal that started, and which was creating a true real-time virtual wind tunnel, is getting closer. Maybe what's saving our neck into this is the development, the incredible development of computers. It's mind-boggling what's going on with computers, especially the graphic computers. We got this new 4700 SGI machine. The nice thing about the SGI machine, as opposed to other machine, is the interconnect, the ability to connect multiple computers at very high speed. The NUMA bus is incredibly fast. So as opposed to normal cluster where you lose a lot of time communicating, in this case you lose more time computing. And the ability to interconnect or interchange CPU and GPU together in a coherent environment. Not just a whole bunch of bucks together, it's a coherent environment. And certainly that's our hope, and we've done it in the lab. I actually tell you the truth, we've done it in the lab already. We got a teraflop connection. I mean, we have two graphic board doing n-body problem in there. We got close to teraflop actually. It's 890 gigaflop. So as you can see here, a lot of the work we've done, I mean, we've done Manuel in this group. We had over the years, 5 years, quite a collaboration, I think. And I think it's been very, very fruitful. And I think, I mean, if the past is, well, it's a French expression. If le passé garant du futur, if the past is a prediction of the future, that's a very bad translation. But garant is a much nicer word. But I think we're going to have much more fun. I think this is going to. We're going. I think seriously, I think we're going to do this virtual wind tunnel, and which is amazing considering we are a very, very small team with not that much money, and I think we're out competing a lot of the big plays. So but in science, it's ideas that counts. Sometimes money, but now that, see, the big guys, what they have over us, outside of much more manpower, is they had those big bucks. But those big bucks are getting cheaper. And the best example of that is those graphic GPU clusters. That a teraflop that is sold actually by NVIDIA, a teraflop machine for about $10,000. So this used to be science fiction at one point. So that's basically it. I mean, like I said, we've had a lot of nice collaboration with EAFIT and with Columbia, and it's always a pleasure to come to Columbia. I really like the atmosphere of Columbia. You're a great bunch of people. That's it. Thank you. There's questions? Oh, yes.
I have two questions. Okay.
The portable microphone. See?
Yeah. I can speak very
Loud, yes.
very loud. Okay, I have two questions. I see two bottlenecks in this kind of access to teraflops technology, and they are first the interconnection bottleneck, because
Between CPUs, yeah. Mm-hmm.
we have a lot of power, computational power, for example, in Canada
Mm-hmm.
and or in Colombia.
Yeah.
But you have
A very small pipe.
Yes.
Yes. Yeah.
And the rate at which the computational power grows is not the same that the rate at that the interconnection.
Yeah.
Okay. Where you grows.
The-
Okay. And the second bottleneck is that people developers that can use this kind of computational power. Okay. I don't know how the application that we have can scale when you get this kind of computational power.
Okay. This is a very good question, and two questions that are actually part of our fundamental design. One thing that we know is, contrary to the propaganda of grid computing, you cannot make computers around the world compute problem unless they actually are not real parallel computation. Even on a normal computer, if you compute with, let's say you take 20 CPU, and if you calculate the amount of time it takes for one CPU, two CPU, three CPU, and actually you can actually see them slowing down because you're taking more and more, like I said, you're talking more than you're actually computing. If you actually do that on a internet network, well, let's say between here and Canada, this very minuscule little pipe of 7 to 10 megabit per second, that's true what you're saying. What we're trying to do, and that's part of the solution server, and that actually is in the technology that we're developing here. This is a block diagram that looks very inoffensive, but is key to answer your question. We believe that what's big stays in the big computer. We then take this information, transform it into human form, and that's where we're transmitting to the client. So actually what we are transmitting to the client is videos. We're transmitting polygons. We're not transmitting massive, let's say the turbine is what, 1 million node. We're not transmitting 1 million node. What we're doing is we have clients that communicate with the server, prepare an image for me, ship it to me. That we've done, and actually I've done it with this particular server here, over ADSL in an airport in Ottawa. I'm able to do on a normal ADSL, even slower than the connection we have between our two countries. And I was able to steer, I was able to visualize, and I was able to control the process of the computer. So this connection here is important. One thing that is important though, and actually something that I cannot do about, which is very important in the design, especially if the design will be with Renata, will be we need not only bandwidth, because bandwidth is just one number in a network. We also need latency. We need to reduce latency. Ideally, even if I only have 1 megabit per second, and I'm using all sort of the compression scheme, ideally, the connection here should be almost like a telephone conversation, a direct path to the connection. In Canada, we have something called user control light path, meaning that when I'm connecting to the supercomputer, UCLP, when I'm connecting to the computer, there's no other packet switching going on. We're dropping the concept of packet switching, and we're saying it's equivalent to a telephone conversation. Because if you would do a telephone conversation like you would do on UCLP, on a normal network, you would have continuously interruption that will actually disturb your flow of understanding what the other person say. I mean, those of you who use Skype sometime when if you have a busy network around, you actually see that. You can the conversation stop for a while, then continue, and so on. That would be totally unacceptable for telephone. So, but that's certainly a really important issue, and that's part of our design. The other question was, can we have this system available for, let's say, a designer, let's say in Medellin, or some guy in some other place in Canada, when he has a good idea, he has his AutoCAD model, and he would like to know if this AutoCAD model is good for bending, or good in certain forces. Well, one of the group I'm working with is called, there's a person who actually is developing clients here that actually are webbable, so they're web access. Eventually, we might have to do that even on our own project. But the clients actually are web accessed, and then basically you take your CAD design, you drop it into a virtual disk somewhere, it gets computed, then the result come back to you, and you can actually start play with that. You can decouple simulation time from visualization time. Visualization time has to be very fast, but simulation time can be basically slower. It's always going to be slower. So we actually, part of the design here, we separated simulation time from interaction time. So typically, when the solution come in, they actually get accumulated into the client. And then we can go back and forth, exploring the data set, as if you give the illusion that we are in real time. But actually, you're not in real time. You are in delayed time because you're having the solution coming in. So it requires, of course, when we don't reach that so-called top compute power. For example, I mean, a teraflop sounds big, but actually with I think 1 million or 10 million mesh element, I don't think we'll do real time. But certainly we can compute it in a reasonable amount of time, let's say 1/10 per second solution, and then we can actually accumulate that in client and then explore that solution. By the time you finish exploring, other solution would have come in. Then you can actually say, okay, stop, this is not a good simulation, I don't like it, start a new simulator. So the other advantage of this here is that you optimizing the use of the supercomputer, which is residing somewhere, because in the past, and actually I've seen many people use, they run big batch for months, they don't even look at the data, and then they look at the data from the viewer, and they run a batch for nothing, because they put the wrong number in the boundary condition. So interactively doing something like this with the supercomputer is also important. But I agree with you, we will have to bring this client here at a level where a small designer can actually use it. And eventually, you can imagine in the world, I mean, once, let's say, Renata managed to get, I don't know, 100 megabits per second, or maybe more, people in Colombia who can necessarily afford those big computers can actually still access them and compute things on them. Those big computers eventually, my feeling is they're not going to be owned by states. They're going to be owned by companies who will actually sell you, okay, I want 100 CPU for an hour and I want to compute certain, and it's going to cost so much. Because why a company or a country should buy those big computers that become obsolete anyway in about 3 or 4 years? Why not buy a computer? And actually, that's true even here. This computer, we didn't buy it. We're leasing it. Because I don't want 4 years, 5 years from now, having an obsolete heater. And that's unfortunate with supercomputers. 4 or 5 years from now, the gradient those supercomputers have relative to the normal computing is not big enough. They give you about a window of about 4 to 5 years. But if you lease them, after 4 years, they replace all the box with a new box. And then I get a service. I'm interested in a service, not buying or owning a machine. I don't care owning this machine. What I want is a service. Gracias.